Hello viewers, welcome back to our series of lectures on chemical bonding. In today's session, we will talk about weak interactions or weak forces. They basically are the non-covalent interactions between different kind of species, atoms, molecules, ions and things like that. The session is planned as follows, that is, to begin with, we will briefly review what we did in the previous session. Then thereafter, we will try to differentiate, we will try to compare the intramolecular and intermolecular interactions or the forces, and then we will try to see that what are different types of intermolecular interactions possible there. And to understand this, what we will do is we will try to talk about different kind of situations, that is, we will talk about the intermolecular interactions between the polar molecules, and then thereafter we will take up polar and non-polar molecules. Then we will talk about the intermolecular interactions between non-polar molecules and then between ions and polar molecules. So, basically this interactions actually is a very broad kind of class of interactions we talk about. So, just to make our understanding simpler, we try to just kind of categorize what kind of interactions we are talking about and what context does it come into play. And towards the end, we will try to sum up what we do in today's session. Okay, let us try to recall what we did in the previous session. In the previous session, basically we explained the formation of ionic solids and introduced the concept of lattice energy, and then thereafter we discussed the theoretical approach to develop an expression for lattice energy and formulated a very famous Bond-Landis equation, which basically theoretically works out an expression for the lattice energy of a crystalline ionic solid there. Then thereafter we discussed the approach for experimental determination of lattice energy, and in the process we discussed in detail about the Born-Haber cycle, which basically is a cycle based on Hess's law of constant heat summation. Okay, that is what we did in the previous session. Let us continue from there and see that because what we have done so far in this whole series of lectures on chemical bonding, we have seen that how do atoms combine to give us molecules, or how do I get ionic solids over there. In all these cases, we talked about different kind of interactions between the atoms or the ions and all. And now we are trying to see that what are the interactions between the molecules, and this differentiation we will try to understand by saying that what do we understand by the terms intermolecular and intramolecular. Basically, the strong forces of interaction within the molecule are called as intramolecular interactions, or interactions and forces are used interchangeably. Let us look at this. So, these are the two molecules of HCl. So, this is HCl here, this is another one here, and we find that within this molecule, this interaction between hydrogen atom and chlorine atom there, this is a strong covalent bond. This is interamolecular interaction, very strong one. And the interaction between this molecule and this molecule, this weakly that shaded, that dotted line over there, this basically is the intermolecular interaction there. These intermolecular interactions basically relatively are weaker forces of interaction between the molecules. So, the point of differentiation is within the molecule and between the molecule. Within the molecule is intramolecular, between the molecules is the intermolecular there. Let us take another example here. Look at these two water molecules here. So, this bond here, that is intramolecular, that this covalent bond between oxygen and hydrogen atom, and this interaction between two water molecules is the intermolecular interaction. And what is very important thing here is that the intermolecular interactions are much weaker as compared to the intramolecular interactions. Let us understand with this example here. If I want to take 1 mole of water and kind of evaporate it, vaporize it, I just need about 41 kilojoules of energy, because vaporization of water essentially means that I have got hydrogen bonded water molecules. I just break that intermolecular interactions and let the hydrogen molecule go to the vapor phase there. So, I just need about 41 kilojoules of energy for that. On the other hand, if I want to break 1 mole of these bonds over there, I need as much as about 930 kilojoules of energy, which is much larger, 20 times plus. So, that is the basic difference. I repeat, intermolecular is between the molecules, intramolecular within the molecule, intermolecular are weak interactions, intramolecular are strong interactions. Okay, let us move further. Now, let us understand that intramolecular forces, which have been talking all these times, is that the strong forces of interaction that hold the constituents together. That means it could be a molecule or an ionic solid or whatever. And in this process, we talked about 3 types of such interactions in this series of lectures. The The first one happened to be a covalent bond. A covalent bond is formed when the atomic orbitals of the two atoms, they overlap and they constitute what is called as a covalent bond over there, very strong interaction. The second thing we talked about was ionic bond formation, wherein there is a transfer of electron from a given atom to another one, and we get ions and which are held together electrostatically in the form of ionic lattices there. And the third kind of interaction which we talked about, which is again intramolecular, that happens to be the metallic bond, wherein we talked about the electron C model and things like that. So, all these are very strong interactions. Now, as against these, let us talk about the intermolecular forces now. The intermolecular forces or interactions are all are electrostatic in nature. Let us understand that. And the strength of intermolecular forces varies over a very wide range, as we shall be appreciating as we proceed further in this lecture today. And we find that to understand, as I mentioned earlier also, to understand intermolecular interactions, we can probably classify them as between polar molecules, then we will talk about between polar and non-polar molecules. We will move further on to the interactions between non-polar molecules, and then ions and polar molecules and things like that. Let us begin with the interaction, the intermolecular interactions between polar molecules. Now, the most significant interaction between polar molecule happens to be dipole-dipole interaction, because we know that the polar molecules have got a permanent dipole, and these molecules interact electrostatically, because there is one dipole there, another dipole. The two dipoles there, their poles, the charges there, they interact through dipole-dipole interaction. And let us see here. So, what you are seeing is there are two molecules of HCl shown over there. So, this interaction here, because this is a charge separation over there, this is a minus delta charge here, minus a plus delta charge over there, same is true over here also. So, the negative charge on this molecule and the positive charge on this molecule, these two come into interaction, and this interaction is referred to as the dipole-dipole interaction. That means this dipole is interacting with this dipole. You can have the reverse of it also. That means you may have that the negative part of this and the positive part of this are interacting, both remain the same thing. Now, this is a very relatively stronger interaction, and though this interaction is electrostatic in origin, its magnitude is much smaller than the ionic bond, because you remember when you talked about ionic bond formation, say sodium ion and chloride ion, that again is electrostatic interaction. Even dipole-dipole interaction also is electrostatic interaction, but the two have got very different magnitudes. The reason for that is that when I talk about the dipole-dipole interaction, this basically is interaction is between partial charges, because we do not have a complete charge. It is not an ion here. We do not have hydrogen ion and chloride ion there. We got hydrogen atom, a chlorine atom, but there is a small amount of charges on them because of the polarity in them, because of the difference in the electronegativities over there. And the magnitude of this charge happens to be, it has been estimated for HCl to be about plus 0.178 and minus 0.178. It has to be electroneutral totally. So, since the interactions between smaller amount of magnitude of charge, so the interaction is going to be weaker as compared to ion-ion interaction, or what is observed in the ionic bond there. And second reason for that is that in case of, when you talk about an ionic lattice, the ions are held together, they are very, very close to each other. As against that, when you talk about dipole-dipole interaction, the molecules are farther apart. That means the distance between the two molecules is much larger as compared to the distance between the two ions over there. And we know that electrostatic interaction is inversely proportional to the distance between the two species which are interacting over there. So, since the distance becomes more here, the interaction is weaker as compared to the ion bond formation there. Okay, that is one very significant aspect of dipole-dipole interaction. The Coulombic interaction actually is proportional to 1 by r, whereas dipole-dipole interaction is proportional to 1 by r6. That means it has got a different proportionality. It is highly dependent on r. When r decreases, this r6 becomes very, very small, the interaction becomes large. That means this interaction is more significant when the distances are small, whereas Coulombic interaction are significant even at larger distances as well, because it depends on only 1 by r and not 1 by r6. Now, we find that the dipole-dipole interactions influence the boiling point of different molecules there. To understand that, let us take an example, say of comparing the boiling points of propane with acetonitrile. Propane is an aliphatic molecule which is a non-polar molecule, and this is a polar molecule, acetonitrile there. We are taking these two molecules because the two have got comparable molar mass over there. And second thing which you see is the dipole moment for propane is about 0.1 dBi, whereas that of estronitrile is as large as about 3.9 D, which is a fairly large amount here. And what you see in terms of their boiling points, we find that the boiling point of estronitrile is much greater as compared to that of the propane molecule there. It is just because of the dipole-dipole interactions. Let us see this picture here. So, estronitrile has got dipole-dipole interaction, that means there are interactions between different molecules here, between the two molecules, whereas in this case there is hardly any interaction between them. They have got interactions, but they are of very weak nature. We will come to that at a later stage when we talk about interactions between non-polar molecules there. That is where it will come into picture. That is called as London forces. Okay. Now, let us go further and see that second kind of interaction. To understand that, we take the example of a interaction between polar and a non-polar molecule, because earlier we talked about two molecules which are polar. So, we have got one dipole here, the two dipoles are interacting. But now suppose I have got a polar molecule and a non-polar molecule, then what happens? One typical interaction which comes into play happens to be the dipole-induced dipole interaction. Let us understand this. We know that the polar molecules have got a dipole moment, whereas non-polar molecules do not have it. So, there are two examples here: HCl, a polar molecule with a dipole moment over there, hydrogen, neutral molecule over there. Now, this has a dipole, this does not have a dipole. But what will happen when the two come close to each other? Let us see that. When the two come close to each other, because of the polarity of this molecule here, because say this positive charge over there, this will try to induce some kind of a charge separation over here, because what will happen is that this positive charge will try to pull electron towards itself and try to repel the nucleus here. So, there will be some slight accumulation of negative charge over here. So, this end of hydrogen molecule will become slightly negatively charged there, and as a consequence, since the overall molecule happens to be neutral, so there will be development of a small tiny positive charge on the other end of the molecule. That means essentially what has happened is, because of the influence of this polar molecule in the neighborhood, this neutral molecule has got some kind of an induced dipole moment in that. And this interaction between this very weak dipole over there, so this induced dipole and the dipole here, the two interact electrostatically, and this interaction is called as dipole-induced dipole interaction. This is a weaker interaction as compared to dipole-dipole interaction. So, this permanent dipole and then this induced dipole, they interact together, and that is what is called as a dipole-induced dipole interaction. Now, one example for this, because we know that oxygen dissolves in water, because oxygen is a neutral molecule, it does not have any kind of charge separation on that. So, how does oxygen dissolve in water, which happens to be a polar molecule there? The answer to that is that when this water molecule interacts with oxygen, it induces some kind of a tiny dipole moment in this. So, there is a polarization here. Because of this positive charge here, this is a negative charge here. So, we get a small positive charge over there, and this end becomes negative, and because of this interaction there, that is a dipole-induced dipole interaction, oxygen dissolves into water there. So, that is an implication of such kind of an interaction there. It is a weak interaction though, but it is significant there. Now, the ease of distortion, because when you try to induce charge separation, so essentially what you are trying to do is, you have a molecule which is neutral, and in the molecule we know that there are nuclei and there are electron cloud over there. So, this, if you want to distort it, if you want to polarize it, the distortion will depend on the polarizability of the atom or the molecule being distorted. Say I am trying to talk about, say oxygen is there, oxygen was neutral, I had a water molecule here. So, this water molecule is polarizing this. This polarization or this induced dipole moment will depend on the tendency of this molecule or atom or ion to get distorted, and that is measured in terms of a parameter called as polarizability, that is the ability of the atom or the molecule to get polarized. And this actually can be seen further, that is, if you look at the solubility of some gases in water, say hydrogen, nitrogen, oxygen, we find that the solubility happens to be 1.6, 19, 43.4. There is a significant difference in the solubilities there, and the reason for that is, in case of oxygen, hydrogen is a very tiny molecule, oxygen is a much larger one. So, in case of oxygen, the electron cloud is quite spread out, it is loosely held electrons over there. So, when this positive charge comes close by, that is of the dipole moment of the permanent dipole is there, so it polarizes it easily. So, the solubility happens to be more over there. That means, it is able to induce dipole moment into oxygen molecule there. Okay, let us move further. Let us talk about the third possibility. That means, I had two polar molecules to begin with, then I had one polar and one non-polar molecule. Now, suppose the two molecules happen to be non-polar, then what happens? Then what happens is, we have a situation what is called as a induced dipole interactions there. Let us understand how do they get developed over there. These interactions are observed both in atoms as well as in molecules there. Initially, to begin with, if I have a neutral molecule, I do not expect any kind of electrostatic interaction between any two neutral molecules, because there is no charge separation of any kind. But if that be so, then how do I explain? Because if say I talk about nitrogen gas, helium or argon, so if these two cannot interact, then no matter what I do to that, the liquefaction of the gases is not possible. Similarly, iodine molecule is a neutral molecule, but iodine exists as a solid at room temperature. That indicates there is some kind of interaction between these molecules is there, and that interaction happens to be induced dipole interaction. Let us understand that. It is very weak interaction though, but it is significant again. Now, this concept of induced dipole interaction was proposed by Fritz London in about 1930, and essentially it was trying to account for that how do non-polar molecules interact, and this force of interaction between two non-polar molecules, which basically is induced dipole interaction, is referred to as London or dispersion forces. It is a very broad term, because practically all species will have this interaction. The only thing is, this becomes significant when we are talking about the non-polar molecules, because in case of polar molecules, you will have dipole interaction. You also will have this London forces, but this will be too tiny as compared to the polar interaction. So, it becomes insignificant over there. But if I am talking about non-polar molecules, then this is the main force of interaction between two species there. So, this is very significant in case of non-polar molecules. Now, this occurs, as I mentioned, in all kind of species, but it becomes significant only when the molecules are neutral, and secondly when the species are very close. Okay. Let us go further and see that how do we visualize this interaction coming into play. Now, suppose I have got two atoms there, two helium atoms there. We know that helium atom is neutral, it does not interact with anything else to begin with. Now, what can happen is, because in case of helium atom there is a nucleus and there are two electrons in the first orbital, 1s orbital. Now, what can happen is, because this nucleus is there in the center and electrons are dynamically moving around there, they are not stationary. So, it may happen that for a given moment, it may happen that the nucleus and electron are slightly away, arranged in a way that there is some kind of a tiny charge separation is there. That means, the distribution of electrons around the nucleus does not remain symmetric, because in this case it is a symmetric distribution. Suppose it loses symmetry for a moment, at that particular moment there will be tiny charge separation between the within the atom over there, and the other atom happens to be as before. But once this atom has developed some kind of a charge separation, or you can say an induced dipole moment has come into this. So, this induced dipole moment in this particular atom here will induce that in the next atom in the neighborhood over there. This also becomes slightly charged. So, this is induced dipole. So, now there two are very tiny dipole. This charge separation will be very small, but significant. So, the interaction between these two is called as induced dipole interaction. Let us look that in case of molecules also. Say two hydrogen molecules here, both are neutral, there is no interaction there, but it may so happen, as we discussed here also, that at a given moment the electron distribution around the two nuclei may not be symmetrical. So, this not symmetrical distribution will lead to charge separation. So, this end becomes slightly negatively charged, this end becomes slightly positively charged over there, and this molecule which is polar now will induce a charge separation in the other molecule also. So, and then the two will interact, but this interaction is called as induced dipole interaction, or dispersion forces or London forces, they all are equivalent terms. Now, this induced dipole interaction is very important, because this, as I just mentioned earlier also, that the strength of dispersion forces, which essentially are based on the ease with which a given charge distribution can be distorted, and they will be dependent on the polarizability of the atom or molecule being distorted over there. So, if I look at two different atoms there, one atom has got a very tight packed electron distribution, it will not be easy to polarize that. As against that, another atom or a molecule which is a big one, large sized molecule, it is easy to distort the electron distribution and then induce a dipole moment in that. So, the polarizability of an atom or a molecule depends on the number of electrons. More the number of electrons, more diffuse is distribution, easy is it to polarize that. Let us look at this picture here. So, we see that the strength of dispersion forces increases with increasing atomic or the molecular sizes. Small molecule here, there is a charge separation, but not very significant, but a larger molecule, the dispersion forces will be more significant over there. That means, the greater surface area leads to stronger London forces, and this actually will be manifested in terms of, suppose I look at a larger molecule, there are two hydrocarbons which are big in size, the two will interact significantly, the melting points or the boiling points will be greater than that in as compared to the smaller molecules over there, and that we can see in this data here. So, look at the methane molecule, a small molecule over there, the melting point happens to be minus 182.5 degrees centigrade. But if you look at CCl4, a larger one, because this is not a polar molecule, all the three are non-polar molecules there, but the size is different. This is a tiny molecule, this becomes much bigger, this becomes much bigger there. So, as the size of the molecules is increasing, we find that the melting points also increase in the same direction there, and this increase in melting points is only because of this so called dispersion forces or London forces or induced dipole interactions there. Okay, let us go further. Let us go further and see that what are the interactions between ion and polar molecule. We have talked about polar molecule, non-polar molecule, non-polar. Now, suppose I got one ion here and one dipole, then what happens? Let us see that. So, as typically such an interaction will be observed between an ion and a polar molecule, and that is observed normally in case of aqueous solutions of ionic compounds. Typically, suppose I take sodium chloride, put it into water, so NaCl dissolves. So, how does it dissolve? We got sodium ions surrounded by water molecules there. So, water molecules are polar, sodium ion is an ion there. So, this ion dipole interaction is what is causing NaCl to dissolve. We will talk about this in detail in the next session, but let us understand this here. So, essentially in such aqueous solutions, the cations and anions are attached or attracted to the opposite ends of the dipole over there. So, in this case, so we have got a positive ion there. So, attracted to the negative end of the dipole over there. So, because there is a negative ends of the dipole here, which is the water here. In this case, this is a negative ion, so kind of attracted to the positive end of the dipole over there. That is, the opposite charges will interact with each other favorably. Okay. Now, the magnitude of this ion dipole interaction is fairly large, and it depends on the ionic charge and the dipole moment over there, because there are two things involved in that. One, we have got a dipole here, one we got a charge on the ion there, and this interaction is electrostatic, because this is charge, this is charge. So, since both are charged, the interaction will be fairly strong. And what you see is that you look at these two systems here. This is sodium ion, this is water molecule, this is magnesium ion, water molecule. So, what you find is this is sodium, it has got certain amount of charge, magnesium has got double that charge, it is 2 plus, this is 1 plus, and water remains the same. So, in this case, this interaction between magnesium ion and water molecule will be stronger as compared to sodium ion and water molecule there, because the charge is more here. Similarly, if you look at this, now in this case what you are saying is that the dipole moment over there. So, interaction between a given ion, say sodium ion, and acetone molecule. Acetone molecule has a dipole moment about 2.91, whereas water has a dipole moment of 1.85. So, since this has got a larger dipole moment, this is a stronger dipole. So, this interaction will be stronger between this ion and the acetone molecule rather than this particular ion and the water molecule over there. So, essentially the point I want to bring home is that this interaction, the magnitude of ion dipole interaction will depend on the ionic charge and the dipole moment of the polar molecule over there. Okay. Now, let us go on to yet another kind of interaction which we did not list earlier. It is called as hydrogen bonding. Actually, hydrogen bonding is a very special kind of an interaction. Effectively speaking, this also falls in the domain of dipole-dipole interaction, but it is put as a special interaction for the reasons because this interaction is of a kind which will be observed only in certain cases. That it is not a generalized kind of a interaction, that it will not be there in all dipole moment, all polar molecules there. It will be there only when it so happens that the hydrogen atom of a polar molecule, that is in a molecule you have got a polar NH, OH or FH bond is there, and we have got oxygen, nitrogen or fluorine atom in the same molecule or a different molecule. That means essentially the basic requirement for hydrogen bonding to come into play is that you must have a hydrogen atom attached to an electronegative atom, number one. And secondly, you should have another electronegative atom to which this hydrogen atom can interact. So, this interaction between the hydrogen atom bonded to an electronegative atom and another electronegative atom, that is hydrogen bond. Let us see in this picture here. So, you can look at this, there are two water molecules here. So, what you have is this is a charge separation on this is a negative charge on oxygen atom there, we got a positive charge on this. So, this hydrogen I am talking about when you say OH, FH and NH bond there. So, for this molecule this OH bond is polar here. So, this hydrogen atom of the polar molecule there, this interacts with another atom which is electronegative. So, it happens to be oxygen over there. So, this interaction is referred to as hydrogen bond, and typically it is indicated in terms of a dotted line or dashed line over there as shown over here. Now, this is another thing, that means you can have such an interaction between the same or different molecules. So, there are two different molecules, they are interacting here. So, here same interaction is shown in a different kind of a graphic there. You got a water molecule, this is in hydrogen bonding with a number of other water molecules there. That is how water is a liquid. Okay, let us go further and look a little more into hydrogen bonding. What we see is that hydrogen bond may be found between two identical, similar or different molecules. Let us understand. Look at these pictures here. So, this shows hydrogen bonding in two carboxylic acid, that means between a carboxylic acid and another carboxylic acid molecule there. So, in this case there are two such interactions possible there, and basic premise is that we have to have a hydrogen atom attached to an electronegative atom and another electronegative atom on same or a different molecule to interact with that. Then this is interaction between carboxylic acid and water, this is between alcohol and water. Alcohol and water are similar molecules there. So, these two are different, these two are identical molecules. So, essentially hydrogen bonding is a very well observed, it is a very common phenomenon which is observed in wide variety of situations there. Let us go further and see that when you are trying to talk about hydrogen bonding, it may so happen that the two interacting molecules which are interacting by hydrogen bonding, they can form hydrogen bonds in more than one way. Look at this, you got an ammonia molecule, you got a water molecule. So, you are having a because this hydrogen is attached to an oxygen which is electronegative, and this hydrogen is coming into hydrogen bond with this nitrogen atom which is electronegative there. So, we got an NH hydrogen bond here, but you can also have a situation of this kind. You can have this H attached to a nitrogen which again is electronegative, and this hydrogen atom gets into hydrogen bonding with this oxygen atom of water molecule there. So, this is an OH hydrogen bond, this is NH hydrogen bond, the two interacting molecules are same in both the cases. So, this is a possibility in case of hydrogen bonding there. Further, it may so happen that the hydrogen bonding can occur within the same molecule. Now, that is the donor part of the thing, that means the hydrogen atom and the electronegative atom to which it is going to hydrogen bond, both happen to be part of the same molecule. Let us look at this. This is orthonitrophenol. So, this hydrogen atom of the phenol here, this gets in hydrogen bonding with this oxygen of the nitro group there. So, this is an hydrogen bond, and same is true here also. So, what you find is such kind of hydrogen bonds are called as intramolecular hydrogen bonding. It is a special kind of hydrogen bonding which is observed, but not in as many cases as what you observe is the intermolecular interaction as I described earlier to you. Okay, let us move a little further and see that this hydrogen bonding is a very special kind of interaction, and it has a significant value to this, because hydrogen bonding, energy of hydrogen bond is of the order of about 5 to 25 kilojoules, which is a reasonably big amount of energy there. Further, these are generally stronger than the dipole-dipole interaction or dispersion forces. Dispersion forces are the weakest one. Dipole-dipole interaction is reasonably strong, but hydrogen bonding sometimes happens to be even stronger than the dipole-dipole interactions. Okay. As regards the significance of hydrogen bonding, because this is a very special kind of interaction, that it becomes all the more significant when you talk about certain biological systems, because hydrogen bonding is very, very pertinent in the case of certain biological systems like say nucleic acids. We know that a DNA molecule acquires a double helical structure there, and double helical structure, the two helices are interwoven there, and there are number of base pairs over there. These base pairs are bonded, the bases here, the nitrogenous bases are bonded through hydrogen bonds over there. So, this is a AT base pair or GC base pair. This AT base pair is formed by two hydrogen bonds over there. In this case, there are 1, 2, 3 hydrogen bonds. So, hydrogen bonds play a very, very significant role in the structure of nucleic acids as they are. Similarly, in case of proteins also, in the secondary structure of proteins, whether we talk about alpha helix or we talk about beta shape, in both the cases hydrogen bonding is the most significant, most pertinent force of interaction between different species of the same molecule there. It is a large molecule, it is a macromolecule. So, within that the number of hydrogen bonds are formed over there, and they are the ones which are contributing to the stability of protein molecules there. Now, this basically is some kind of a summary of these interactions there. So, we talked about induced dipole interaction or London forces, they are the weakest one there. So, between the two molecules we talked about here, and they are very short range, because they become significant only when R is very, very small, but at larger values of R they do not really have any significant contribution to the overall system there. And then we got induced dipole interaction, that has a magnitude of about 2 to 10 kilojoules per mole. Short range, that is the interaction we talked about between oxygen molecule and a water molecule there. Then ion induced dipole, it is about 3 to 15 kilojoules. Medium range there, so R is to about 4 here. So, we got a molecule here, a dipole and an ion over there, the two are interacting there, or we can have a dipole-dipole interaction, which is about 5 to 25, similar to what we have in case of hydrogen bonding there. So, hydrogen bond is, it can even go to from 10 to 40 kilojoules in some cases. So, that is the kind of interaction we talked about, and then we also had ion dipole interaction, which is a long range interaction there. Okay. Now, let us sum up what we have done today. What we have done today, basically we started by reviewing the contents of previous sessions, and then thereafter we differentiated between intermolecular and intramolecular forces of interaction, because there are two terms have to be understood very well. Having done that, we moved on to explaining the intermolecular interactions in wide variety of situations, and they happen to be between polar molecules, between polar and non-polar molecules, non-polar molecules, and between ions and polar molecules. And lastly, we did take up hydrogen bonding as a special case of dipole-dipole interactions over there. Now, next, in the concluding part of our series of lectures on chemical bonding, we will talk about dissolution. That means, how do solids dissolve? Typically, we will focus attention primarily onto ionic solids dissolving into solvent systems over there. Typically, we will talk about water as there as a solvent over there, and that should be taken up in the next session. Thank you.